Cryptanalysis. We will have 5 talks with a 10-minute break after the third talk. The first talk of the session is entitled Truncated Boomerang Attacks and Application to AES-Based Ciphers by Augustin Barian and Gaëtan Laurent, and the talk is given by Gaëtan.
Thank you for the introduction. So it's a joint work with Augustin, who is a PhD student working with me. And so I will talk about truncated boomerang attacks and application to AES-like ciphers. So you probably know that the AES is the most widely used block cipher today, so it's really important to understand its security. And not only the AES itself, but also components of the AES, because they're reused in many different contexts, because they're now very efficient in hardware. So we need to do cryptanalysis in order to understand the security, because that's how we study the security in symmetric cryptography. So there are many different cryptanalysis techniques, and in this talk I'm going to talk about the boomerang attack, which is a technique that was proposed in 1999 by Wagner. And the idea is that instead of analyzing the full cipher, you split it in 2 halves, E0, E1, and you look at 2 differentials. So you have a differential delta in to delta out through E0, and another differential nabla in to nabla out through E1. And we will denote the probability of the first one as P and the second one as Q. And so you assume you have this decomposition of your cipher, and the idea in the boomerang is to use those 2 differentials that have been built independently. And for this, we're going to use both an encryption oracle and a decryption oracle, so it's an adaptive attack, and we're going to build quartets. So let me try to explain a little bit more how it works. So you start with a pair of plaintext, PP prime, with the difference delta in. You encrypt them, you get 2 ciphertexts. But you don't look at the difference between those 2 ciphertexts because you cannot say anything useful about them, because you don't have a differential through the whole cipher. So instead what you do is that you're going to shift your ciphertext into new ciphertext, C bar and C bar prime, by applying the difference nabla out. And then you decipher those new ciphertexts, and you get P bar and P bar prime. And now you're going to look at the difference between P bar and P bar prime, and you check whether it is delta in or not. And if it's delta in, we say that the boomerang returns, because you start with your pair of plaintexts, you throw them inside the cipher, they come back, and you get the same difference. And this is interesting because there's a good probability that it actually returns, and you can estimate the probability as P square Q square, and you get this just by looking at the 4 different parts of the cipher. And in fact, this gives you a distinguisher, because if this probability is high enough, if it's higher than 2 to the minus n, then you can just repeat this with many different pairs, and if you see one pair that returns, it means you have your block cipher and not a random permutation. So in this talk, I'm going to look at the boomerang cryptanalysis, but in the context of truncated differentials, so it's slightly different. It's actually not a new idea. It's already in the paper by Wagner in 1999, but we're going to do it in a more systematic way, and we're going to look at how to use structures on the plaintext and ciphertext side, and how to do distinguishers and also key recovery. And the goal is to obtain generic formulas, and then when we have a nice formula, we can apply it to many different attacks. And we're going to revisit a previous attack on 6-round AES, and we will improve the complexity from 2 to the 71 to 2 to the 61. And we can also apply our framework to various constructions, Kiazu, TNT, and Deoxys, and we're going to obtain the best attacks on those ciphers. So let's start with the truncated boomerang distinguisher. So first, what is truncated differential cryptanalysis? It's basically a generalization of differential cryptanalysis, but instead of looking at the full difference in the state, we truncate this information and we only look at some partial information. For instance, we only look at what bytes are active or inactive. So we only know whether the difference is 0 or non-zero. And then we can track this information through the cipher. After each round, we look at each byte, whether it's active or not, and we can build a tray like this and compute the probability. So in this talk, I'm going to use a slightly different view. I will only look at sets of differences. So we have a set D in and a set D out for the output. And we look at the probability, if you take a random difference in the input set, that after the cipher, you get a difference that is in the output set. So we denote this probability P forward, and it's the probability for a random delta in inside the set that encryption of P plus delta in is in the set D out. And you can also define the probability in the backward direction. And in general, it's not the same. When you have a truncated trail, you can have two different probabilities. So to give you an example, we can look at the AES, because this will be an important example in this work. And there's a very well-known 3-round truncated trail. And the idea is that you start with a difference in one diagonal. So you have 2 to the 32 possible differences that are active in this diagonal. So the set of input difference is of size 2 to the 32. And you look at what happens when you go through the cipher. And so after sub-byte, you still have the same cells that are active. After shift row, your diagonal moves to a column. And then you have a mixed column operation. And with some probability, you will have only one active cell after mixed column. And this happens with probability 2 to the minus 24. And if this happens, then with probability 1, you can track how this evolves in the next round. And after one round, you get an active column. And after a third round, you get a state that is active in all cells, but not with a random difference. This difference must be in a set of size 2 to the 32, because before the final mixed column, you only have 4 active cells. So you have this trail. You start from a set of 2 to the 32 difference, and you end with a set of 2 to the 32 differences, and you have probability 2 to the minus 24. And if you take it backwards, you have something similar, where you have a probability 2 to the minus 24 to collapse inside a mixed column. So this will be the basis of our attacks, and it's interesting to see that looking at truncated trail, you get a probability that is better than if you would try to fix all the differences in the middle. So how can you use this in a boomerang attack? Well, it's very similar to the boomerang with normal differentials, but now everything is truncated differentials. So you start with a pair of plaintext with a difference delta in, but we don't fix this difference delta in. We can pick any difference in the set of good differences. Then we encrypt them, we shift the ciphertext, and again, we don't shift by a fixed value. We can pick any value in the set of good output differences. And in particular, we can pick different values from nabla out and nabla out prime. And then we decrypt this, and when we get the new plaintext, instead of looking for a fixed difference for the returning values, we allow any difference in this set delta in. And now when we analyze this construction, we can compute the probability that the boomerang returns, and we get a formula like this. The probability will be P forward times P backwards time Q backwards square time R. So it's similar to the basic case with normal differentials, but it's slightly different because you have this R times that comes as an additional factor, and also you have to look at which direction you use for each trail. So why do we get this formula? Well, we start with a pair PP prime, and with some probability, when you encrypt them through E0, you get XX prime with a good difference delta out that is in the set that you want to reach, and this happens with probability P forward. Then you shift your ciphertext, you decrypt, and then we can look at what happens in the bottom part. And with some probability, your difference nabla out will go to a difference nabla in that is in the set following the trail, and this happens with probability Q backwards. It's the same thing on the other side of a boomerang. And then if you have those three conditions, so delta out is in the set, nabla in is in the set, nabla prime in is in the set, and then with some probability, the fourth side of this square will also be in the good set. And we denote this probability R, and in general, you can compute it if you have vector spaces, you can compute it as the intersection of some vector spaces. But in fact, in all our application, we found out that the only case where this works is if nabla in is actually equal to nabla prime in. Because then you just have delta prime out equal to delta out, and then of course it's in the set, because delta out was in the set. And then finally, you look at the last part. When you start from x bar, x prime bar, you decrypt then, and with some probability, you end up in the set. And so you have those 5 events, and if everything is satisfied, and if we assume that everything is independent, then we obtain the probability of returning. And so that's a very important formula, and it will be used in all the remaining. So now to build a distinguisher from this probability, we're going to use structures, because that's something we do every time we have truncated differentials. And the idea is that if you start from one plaintext, you build all the plaintext with differences in the set, and we assume that the set is a vector space, and then you can take any 2 values, any 2 plaintext in this set, and their differences will also be in your good set. So you build a set of some size, and then you get a quadratic numbers of pairs that you can use for your attack. So you gain a lot thanks to this property. And we can actually do the same thing for the ciphertext. So you start from one plaintext, you build a structure, you encrypt the structure, and then each ciphertext in your structure, you can shift it by many different values on the ciphertext size. And then you take all those values and you decrypt them. So in the end, you get a structure of size of the input difference times the size of the output difference set, and you have a number of quartets that you can use, which is the square of this. So you really have a very strong structure effect in this attack. And this is something that wasn't really done properly in previous works. And so to give you an example, we can apply this to build a 6-round attack on the AES. So we start from the trail that we've already seen, and we have those parameters that we can just compute from the trail. And so in one structure, we have 2 to the 64 values, because we have 2 to the 32 choices in the plaintext, and then each ciphertext is shifted in 2 to the 32 different ways, and then we decrypt everything. So this means in one structure, we have 2 to the 127 possible pairs to look at, and those will be candidates for quartets. And the probability of returning, when you compute it with the formula, you get 2 to the 128, and this means on average, you expect 1/2 good quartets in a structure. So that's not too bad. What's slightly annoying is that, in fact, you have many wrong quartets, because the filtering you get is only 96 bits of filtering, because any difference on the returning side that is on one diagonal will be considered as a good difference. So you actually have many false positive. You have 2 to the 31 in each structure. So that's a little bit annoying, because if you have the AES, you expect 2 to the 31 plus 1/2 quartet that's returned, and for a random permutation, you have 2 to the 31. So that's very close. But you can distinguish them if you repeat enough time. If you do a statistical analysis, you see that you have to repeat about 2 to the 32 times, and then you can distinguish. And this means you have a distinguisher with complexity around 2 to the 96, up to small factors, depending on the success rate that you want. But that's really nice, because we can use this property for a 6-round distinguisher on the AES, and it's a really simple distinguisher. More generally, you can do the analysis based on the parameters. And what's important is the signal-to-noise ratio, which is the ratio between the probability of a boomerang and the random probability of returning. And if the signal-to-noise ratio is high, then the attack is easy, because all the quartets are good. And if the ratio is low, then you have to repeat the attack with a factor 1/sigma. But we have a generic formula, and we can compute the complexity, and we can deduce the data complexity based on the size of the structures. So now let's see how we turn this into a key recovery. So usually the way you build a key recovery is you add some rounds at the top of your distinguisher, and the complexity usually goes up. And what we do here is different. We keep the same number of rounds, but we try to extract information from the quartets that seem to follow the boomerang. So the number of rounds will be the same, but the complexity will go down. So, so the idea is we collect many quartets, we assume they follow the trail, and then we extract information about the key. So if we are in the case where all quartets are good, that's easy, you just get the key. If we are in the case where the signal-to-noise ratio is low, you have to collect many quartets. Most of them will be wrong. But if you build counters for each key candidate, you will still get a signal, and the right key will come up after some time. So looking at the 6-round example again, how do we extract key information? Well, we can look at the first round, and when we have a quartet, we have a value pp prime that we assume follow the trail, and based on this value pp prime, we can get information from the diagonal of the first key, because we know that after one round, we want the difference to collapse to just one active state, and this is determined by just the first diagonal of the key. And on average, we expect that 2 to the 8 key candidates out of 2 to the 32 will satisfy this property. And we can do this for pp prime. And because we have a quartet, we also have another pair that can be used to extract key information. That's the pair p bar prime. So we get a different set of 2 to the 8 candidates. And when we intersect them, on average, we expect 2 to the minus 16 candidates. You can do the same on the last round. And in total, you get 2 to the minus 32 candidates for 64 bits of the key. So this means when you have a wrong candidate, usually you get no key candidate. So you can actually recognize that it's a false quartet. And if it's the right one, of course, you will get the correct key that comes up. So starting from S structures, we have seen already that we have S times 2 to the 31 returning quartets. Most of them are fake positives, but they actually only suggest a small number of wrong keys, because most of them don't suggest any key. So we have S over 2 suggestions for wrong keys. And we have S over 2 right quartets, and this gives S over 2 suggestions for the correct key. So it's actually very easy to recognize the correct key, because half of the suggestions are correct. So we get a key recovery attack with complexity around 2 to the 64, with small factors depending on your success rate. So we can also do the analysis in a generic way, and we have a generic formula for the key recovery part. And what's important here is that the signal-to-noise ratio gets better, and you have an extra factor 2 to the kappa over L, which comes from the parameters of the key recovery phase. And again, if your signal-to-noise ratio is high, the attack is easy. If it's low, you have to repeat a bit more, but in all cases, we get something that's better than the distinguisher. And then, to summarize, we can do this on 6-round AES, and we get actually some really nice results, because there's been a lot of work recently on 6-round AES. There's been many recent papers on distinguishers, and we can see now that the truncated boomerang gives a very nice distinguisher that's competitive with a previous work, even though that's actually a very old technique. When we do key recovery, we also get a really interesting result. It's not the best result, because the partial sum technique is still the best attack on 6-round AES, but it's still competitive with recent work. And we can also use it in the context with a secret S-box, which is a nice context where very few attacks can be applied, but the boomerang actually works. So I will quickly talk about other applications. So the first one, which is quite nice, is on Kiazu. So Kiazu is a tweakable block cipher based on the AES. And because it's a tweakable block cipher, you can have differences in the tweak that will be introduced inside your state. And because of this, you can have a 4-round truncated trail with one extra round in the middle that is completely inactive, because the difference in the state cancels with the difference from the tweak, and this gives you 1 round for 3. So this trail has probability 2 to the minus 32. You can compute all the parameters, and actually you just have to take the generic formula that we get, and you obtain the complexity of the attack, and it's about 2 to the 80, with some small factors, so maybe 2 to the 83 if you want actually a good success probability, and that's much better than the previous attack, which was also using the same type of techniques, boomerang with truncated trails. But by doing this systematic analysis, we actually get much better results, because now we can integrate a lot of tricks inside, and we get a nice improvement. So another application is Deoxys, which is another tweakable block cipher based on AES. In this case, the trails are quite messy, so I will not show them. And in fact, in previous works, they've been obtained with a MILP model. And we're going to do the same. We have built a MILP model that integrates truncated characteristics. And what we do is that we put all the parameters for the key recovery inside the model, because now we have a nice formula, and all the parameters are given directly by the trail. So we can get the data complexity of a key recovery, and we can give this as an objective for the MILP, and we get attacks that are better than previous works. And finally, we also looked at TNT AES, which is another construction where you do just 6-round AES, then you XOR a tweak, 6-round AES, you XOR the same tweak, and again 6-round AES. So it's a very simple construction. And it's interesting because it's basically using 6-round AES as a building block. And I've shown that we have a distinguisher on 6-round AES, so it's interesting to see whether we can apply it in this context. And actually we can, because we can build boomerangs for the middle part using the tweak. And we get something that's not exactly an attack, because you can see it's actually a distinguisher with complexity 2 to the 127.8. So I wouldn't call it an attack, but it's still a nice result showing that the distinguisher can be applied and does something. And I think I'm out of time, so I will stop here, but thank you for listening.
I'm not sure we have really time for questions, except if one knows a very short question calling for a very short answer.
Just one very quick question. For example, for the 6-round AES, so I understand that you start from 6-round distinguisher and then try to integrate the key recovery inside to reduce. So did you compare with trying to get like 3 rounds and 2 rounds boomerang and then putting a classical kind of recovery on top of this? And how this will fare compared to?
Okay, yeah, that's a very good question. So actually, if you do it in a more classical way, you get essentially the same results. But integrating everything gives us a nicer formula, and it's easier to analyze it in general. In particular, to build the MILP, it's much easier to use this formula directly. But you can also see it as a more classical key recovery, and if you do it properly, you get essentially the same result.
So, thank you. Let's.
Thank you.
Yeah. Thank you. So, yes, the next talk is entitled Better Steady Than Speedy, Full Break of Speedy 792 by Christine Agboura, Nicolas David, Rachel M. Boissier, and Maria Naya Plasencia. And the talk is given by Nicolas David.
Thank you for the introduction. So today in this talk, I will present you a full break on the main version of Speedy. So this attack actually is a differential attack. So the first thing that we'll do is I will introduce some basic concept about differential cryptanalysis to set up notations. Then I will introduce you the specification of Speedy. And finally, we will get into the details of our attack. So differential cryptanalysis. So let's assume we have an encryption function EK that can encrypt plaintext P into ciphertext C. And what we can do is add some input difference in P and get some out of plaintext P plus delta in, and we can try then to witness whether we get delta out as output. And if we can witness like this propagation of difference very often, let's say more often than what we would obtain for a random permutation, then we can use this to build a differential distinguisher. So now, let's assume we have a differential distinguisher for some rounds of the Blockcipher with an underlying probability to the minus p. What we can do is extend it both at input and output into key recovery rounds. And what we would obtain is 2 sets d in and d out that are the propagation of delta in and delta out respectively. So we note 2 to the d in the size of d in, and 2 to the d out the size of d out, and 2 to the n is the size of the internal state. So with this, we can build a differential attack that splits into three main parts. So the first part is data generation. So what we do here, we just do a call to the encryption oracle to get some data. So the complexity of this step is directly related to the underlying probability of the distinguisher. So it's 2 to p plus 1. Then once we have gathered data, what we want to build is pairs that satisfies the input and output sets, so that follows the difference in the in input and the difference in the out in output. And so this step is called pair sieving, and the complexity here is both related to the probability and also to the size of the sets, the in and the out. And finally, once we have these differential pairs, we can perform key recovery and recover actually the encryption key, and the complexity of the last step is related to the amount of pairs we've gathered in the previous step. And what we want to do, if we want to have an efficient attack, is to minimize the overall cost, which is the sum of the complexity of the 3 terms. So that's it for the main part of differential cryptanalysis, and now I'll get into the specification of SPD. So SPD is a block cipher that was designed by Leander, Moss, Moradi, and Rachou Ladeh, and was introduced in CHES 2021. So the internal state and the key can be represented by an array of 192 bits, that is 6 times 32 bits. Regarding the key schedule, it's just a bit permutation of all the bits. And for the round operation, there are 3 main round operations. So the first one is SB for SBox, which is an SBox that is applied on every row. So it's a 6-bit SBox. Then there is SC, that stands for shift column, that rotates the column by a different outset depending on the number of the index of the column. And the last one is mixed column, which is a linear operation that is applied to every column. So the round function of SPD displays as follow, and as you can see, there are 2 XBox layers per round, so it's pretty heavy round function. And note that for the last round, the 2 last linear operations, so SC and MC, are omitted, and there is an extra weighting key addition added. So there are different versions of SPD, depending on the number of rounds. So it's very SPD 5, SPD 6, and SPD 7, and there are different security claims depending on the versions. So in our work, we managed to improve the cryptanalysis on every single versions. But what I want to focus today is on our attack on SPD 7, because it's where we managed to actually break the security claims both for time in data and also another security claim that the authors made in the original paper, which said that the attacker cannot add more than 1 round to extend the distinguisher, because actually in our work we managed to add 1.5 rounds for key recovery. So now let's get into the details of our attack. So on the version SPD 7, so 7 rounds of SPD. So the first things I want to discuss about is how we build the differential trail. And the starting point of that is by looking at the differential table of the SBox, and more precisely what we want to look at is the propagation of 1 bit input to 1 bit output difference. And what we can see is that we have a high probability for lots of them. So it's a maximum probability. When we see a 4 here, it's 4 times 2 to the minus 5. So that's yes. So that's the starting point. We can actually try to build our distinguisher using this kind of transitions. And so with this, now we can try to actually compute some good trails. And the approach would be to pre-compute 1 round trails and chain them. And the very first step will be to build a table around the mixed column operation. So we gather pair X, MX, so that's there is at most 7 active bits. So we store these into a table. And then what we want to do is look at trails that have some that follow some condition. So the first, so what we want is that we have a single active column at the beginning and at the end of the round, and that also that after the SBox there are at most 2 active bits per row, so that the complexity doesn't explode. And yeah, so chaining all this by computing all this 1-1 trail, we managed to build 5 round differential distinguisher, probability to the minus 183, and this is it here. So I want to stress something that happens in the very end here. So note that we have here some bits that are in gray. It's because we allowed some, we could have asked for a transition from 1 bit to 1 bit here, but we allowed some trade-off in the probability, so we allowed some liberty, so that some freedom, so that in the output we touch like only 7. It make only 7 active columns, active rows. Sorry. And yeah, this is a trade-off that we use here to reduce the complexity of the probability. I mean, to have a better probability. Sorry. So with this distinguisher, we have another probability to minus 183. We can add some key recovery rounds. So we add half a round in the output and 1 round in the input. And this is what we get. So at that point, since we have the probability of the distinguisher, we already know the complexity of the first step, because it only depends on the probability. And now I want to discuss about the second step, which is of the differential attack, which is perceiving. So one thing that we can do right now is just focus on row 24 in the input. So what we can see is that there is a transition like this present in the, when our key recovery round. And the question we can wonder is which input difference can follow such transition, because some difference can actually cannot actually verify this transition. So what we can do is compute the set of difference that follow this, and then when we would build, we can restrict, if you want, the in to a bit, so that we discard all the pairs that do not follow this transition. And this result is in the sieving, and if we do it for all the line, we would obtain a total sieving of 2 to the minus 11. So, right now we can take a look at the complexity we got so far. So, the complexity for the first step data generation is fine, it's 2 to the 184. However, the complexity for a second step is a bit too expensive. So, what we need to do now is to find a way to reduce the second step, and we will do it by finding complexity trade-off that will increase the value of P, since we have some room, but drastically reduce the value of T in. So I want right now to take once again a look at our key recovery round. And as you can see here, all these 3 active bits here are activating actually a lot of rows in input, all the pink rows. And what we want to do now is actually have some kind of control on this propagation here to reduce the amount of rows that are touched. So what we want to consider now for our input set of difference is to have the differences that will activate at most 3 rows. And so as a consequence, we'll add 2 to the minus 69 to a factor to our probability, but this will drastically reduce the size of the input set. So once we do this transformation here, we obtain the data complexity of 287 and the perceiving complexity of 286. So now we are happy because we have 2 terms that are somehow balanced, so that's pretty good for our to minimize our complexity. Okay, so now that we discussed the 2 first steps of the differential cryptanalysis, we want to look into the very last step, which is key recovery. So the first thing we can see is that there are some bits that we can recover for free, looking at the output. Since we know we know the difference in the plain text in the output, then there is some key which is added, and we know that that the S-box, the very last S-box, we have a precise difference. So we can recover the key because it would be the plain text that would allow the transition. So first, we have already some free bits regarding the output. However, it does not give us the whole key. So we need to perform some technique to recover the key for the bits that we yet don't have. And we will use a technique called the early abort. So it consists as follows. So first, we consider a propagation condition. Then we guess the needed key bits that we don't know yet. So it costs us to the GI to guess. And then we discard all the pair key that do not follow the condition. So that's a filter to the minus fi. And then we repeat the process until we know the whole key. So the complexity for this will look something like that. And since if you look at the complexity, we see that all the terms 2 minus gi minus fi will multiply themselves. It's important if you want to minimize this complexity, this term, that to sieve as soon as possible. Okay, so that's the technique we will follow. And something else that we will use to have efficient key recovery is a technique called parallel matching that was introduced in Crypto 2011 by Mariana Placentia. So I won't discuss exactly the exact algorithm, but basically, if you have some data which is stored into two lists, and you want to find some elements that satisfy your relation on the Cartesian product of the list, you can actually perform something which is pretty efficient if you can split your relation into a smaller relation. And this is something that we used, and you will see an example. I will present an example of that just after. So now we take a look again at our key recovery round for the input, and what we see is that the condition that will filter the most are the condition around the second Xbox because I represent 6-bit filter, and so we want to take a look at them if we can use this condition as early as possible, we will have a key recovery that is very cheap. So all the key recovery around, all the transition around the second Xbox look like that. And what we can do here is actually pre-compute the state before the second Xbox, so on the left side here, by computing S-1, using the Xbox. So we would get some pairs like this, and then instead of trying to make a match on the difference after the Xbox, what we want to do is make a match on the pairs before the Xbox by looking at the pairs we pre-computed like this inside the table. So let's now take an example regarding the row 17, 18, and 19. So for now, let's assume we know, before the shift column operation, the row 18, 19, 21, 22, and 23. As we can see, we would have some partial knowledge for round 17, 18, and 19 after shift column operation. And since we are matching on pairs, for row 17, for example, we will know an amount of 2 to the 4, so we know 4 bits, but since it's pair, so it's time 2. So for row 17, in the end, we have 2 to the 6 possibilities, but we are trying with 2 to the 4 times 2, so it will result in a filter of 2 to the minus 2. And we can do this for all the 3 rows, 17, 18, and 19. It results in an overall filter of 2 to the minus 8. So this is typically a relation when you look at the 3 rows at the same time that split into 3. So for each of the rows, for row 17 is one relation, for 18 is another relation, etc. So this is typically somewhere where we can use parallel matching. And something I want to stress here is that we manage by using pre-computing the pairs, we manage to sieve here without knowing the whole row for any of these rows. And this means that we need to guess fewer keys to start sieving. And now, so I assume before that we know some rows, so 18, 19, 21, 22, 23, etc. And to record them, actually we build this table here that just summarizes the knowledge we already have from the output and the amount of key we are left to guess. And this we can actually write down the cost we are left to pay. And by optimizing this, we can see that an efficient way to actually perform the match here is to guess 19, 21 in one side, and on the other side 18, 22, and 23, and perform a parallel matching. So this helps us and gain some complexity here. And for the remaining rows, we just do sequential key guessing from bottom to, so from row 24 to row 2. So as a conclusion, I would say that even though differential attack is some pretty well-known type of cryptanalysis, if you are very careful at every step, you can actually build a very efficient attack. So here we use one-to-one S-box transition. So we have a high probability trail. We used some sieving techniques and trade-offs, and the use of refined key recovery. So we managed to break to contradict the denier claims. And thank you for your attention.
Thank you. So we have time for one question. Any question? If not a very small question, yeah. I had the impression at slide probably 18 that it's a chosen ciphertext. One is in a chosen cipher. One starts from the
exactly.
Well, would the performance have been very different in the setting where plaintext are?
Okay. So yeah, actually, it's more efficient to perform the attack in the decryption way. That's your question?
Yes.
Yeah, and the reason for that is that when we use this trade-off here, it's better to do it the decryption way, because if we want to use this, we cannot build our data using structures, and that's a bit annoying. So that's why we use it the decryption way. Okay. Yeah.
So. Thank you again.
Thank you.
We are synchronized with the other room. So, the next talk is entitled Exploiting Non-Full Key Additions, Full-Fledged Automatic Demirci-Selçuk Meet in the Middle Cryptanalysis of Skinny by Dan-Ping Shi, Si-Wei Sun, Ling Song, Lei Hu, Qian Yang, sorry for the dubious pronunciation, and the talk is given by Dan-Ping Shi.
Okay, thanks for the introduction. Hello everyone, I'm Dan-Ping Shi. This is a joint work with Si-Wei, Ling, Lei, and Qian. This talk will consist of 3 parts. First, I'd like to give a brief description of the Demirci-Selçuk meet in the middle attack. This attack was first introduced in 2008. Since then, many improvement techniques are introduced. To find this attack efficiently, a dedicated search algorithm and a constraints programming-based approach are produced. To construct a distinguisher, 2 sequences of positions should to be found. Assume A is a sequence of positions. Construct a delta A set of several plaintexts. These plaintexts are all different in positions specified by A and all equal in other positions. Assume B is a sequence of the output positions. Consider the ordered sequence of differences between all ciphertexts Ci and C0 in positions specified by B. For a block cipher, the sequence is usually uniquely determined by several internal parameters. So if the size of the values space of the internal parameters is less than that for a random sequence, the distinguisher is a construct for the pair of A and B. Then an attack can be mounted based on the distinguisher. A cipher can be split into 3 parts. The pre-computation phase will construct the distinguisher on the second part, and a lookup table will be built to save all the values that the sequence may take. The online phase is 2 gates involved round keys to identify a delta asset for the distinguisher and compute the value of the sequence. Check whether the value in the lookup table obtains the candidate. In the following, I'd like to give examples of concepts on a toy cipher. The toy cipher has 4 bytes block size, and the linear layer is to update the states by left multiplying a binary matrix L. A has the position S03, B has the position S31. Then the sequence at 31 can be uniquely determined by 7 internal parameters. For each pair Pi and P0, the difference is active at S03. So with the value of P0 at S03, through the 1 round encryption, the input difference of round 1 can be deduced, and the difference is inactive at S13. So iterate this process with the 6 remaining internal parameters. The sequence can be determined. So the sequence can take at most 2 to the 56 possible values, where it has 2 to the 2040 possibilities for a random sequence. The main bottleneck improvement technique is the differential enumeration technique. Assume P0, P prime conforms to a truncated differential tree on the left figure. Then construct a delta asset from P0. Many values of the internal parameters are not reached. For each differences in the for each input and output difference of the S box in the red box can be determined by the difference at S03, the output difference at S31, and the value of P0 at the 4 active bytes. So the 7 internal parameters are reduced by 1 byte based on the differential enumeration technique. Some round keys can be deduced from these internal parameters. The key-dependent sieve technique is to utilize the relations on these round keys, while key bridging technique is to utilize the relations on the keys involved in the key recovery phase. The tweak difference cancellation can control the tweak difference to cancel a state difference. As our framework is developed from the CP-based approach for the basic attack, I will describe this CP-based approach. 3 type of variables are introduced for the basic attack. Type X form a forward differential tree. For each P and P prime, if their difference at positions among A bar I equals 0, then their difference at positions among a bar I plus 1 should be 0. Informally, the type X follows the differential propagation rule with probability 1. Type Y form a backward determination tree. For each pair P and P prime, their difference at the positions among BI plus 1 can be uniquely determined by the knowledge of the positions among BI. Informally, type Y describes the positions that have effects on the output sequence, while type X describes the activity of the difference for each pair in the delta A set. So for a specified delta A set, the output difference can be uniquely determined by the positions where type X equals 1 and type Y equals 1. Type Z variables are introduced to describe these internal parameters. The CP-based approach for basic only capture on the basic attack. Some improvement techniques still rely on manual work. In this paper, we will give a full-fledged automatic framework. This is a high-level overview. 3 type of variables for the basic distinguisher. And to describe the differential enumeration technique, 3 type of variables are introduced. One describes the traditional truncated differential tree, and the other 2 will describe the internal parameters based on the differential enumeration technique. The key 2 new type of variables are also introduced to describe the key dependency technique. These internal parameters described by the 2 type of variables introduced in differential enumeration technique will be unified by a new type of variables, and the other one are introduced to describe the deduced round keys. As type X variables describe the differential propagation, so the type variables are also introduced for each tweak cell. The methods for modeling the key recovery phase is similar to previous CP-based approach. In this paper, we just needed to model the phase of obtaining a pair conforming to the truncated differential tree. To model the differential enumeration technique, type GT variables are introduced, and type GT follow a type T-based backward determination tree. It is a little different from a backward determination tree, because in this case, P and P prime conforms to a truncated differential tree. For example, the difference at these 3 bytes should be affected by all bytes, all input bytes, but in the truncated differential tree, the difference at 3 bytes are inactive, so only type GT at S00 equals 1. A type T-based forward determined tree is also presented in the opposite direction. Denote Rm be the round where the 2 trees meet. Then all the differences at these red sides, at these red bytes can be determined by several internal parameters, and these internal parameters can be described by type GT variables. with the differential property of S-box, the value of P0 at these red bytes can also be deduced. So to combine with the basic attack, type GT in round RM will be initialized by type T and type Z. Among all the internal parameters that are described by type Z, some are bounded by the type GT variables. So in order to describe the remaining internal parameters, new type GZ variables are introduced, and all the internal parameters are described by type GT and type GZ variables now. Some round keys can be deduced from these internal parameters. In order to uniformly describe the internal parameters, the type GZ and type GT variables are unified by a new type of V variables. And we should introduce type K variables to describe the deduced round keys. And type key variables should be constrained by type V variables according to the key addition operation. Then the relations of the round keys for a specified cipher can be included in the model dynamically. For a tweakable Blockcipher cipher, the delta A set is a plain text tweak combinations now. The tweak difference can be controlled to cancel the state difference. So the propagation rule through the tweak addition it's different for the round with tweak difference cancellation from the forward differential propagation. And the constraints for this round can be seen in these left equations. And the framework are applied on Skinny. Typically, Skinny the round function of Skinny consists of 5 operations. Note that partial states of each round are updated by the tweak keys. So the states between 2 consecutive rounds are not totally independent. And the linear layer with the so we introduce the non-4 key addition technique. Each linear layer with non-4 key addition can be simply expressed by this equation. And the internal parameters where type V equals 1 should be considered. For each variable in the subset, the variable can be expressed in the form of x4 to x7. Then the rank of the coefficient matrix is the degree of freedom of this subset. So we can also obtain the reduced bias. All techniques are integrated for the search for the best attack on Skinny. The results are summarized in this table. All the demercy cell meter in the middle attack results are improved. Thanks for your attention.
We have time for questions. Are there any questions from the audience? perhaps. I have a very small question. In the table of slide 21, it seems that to me that sometimes the memory complexity is slightly above the time complexity of the best attack.
Yeah.
Does it come from the fact that memory is not really counted as a part of the time? It's considered a smaller operation than.
Yeah, we consider the time complexity most.
Okay, of course, time is.
Yeah. Okay. Thank you.
Thank you. Okay, so let's thank again. And I think that we have something like 5 minutes for swapping. It's not a real break, it's just to give people, I think, an opportunity to swap from tracks.